So, in the last lecture we were looking at applications of potential flow, specifically the flow metering in two applications. One was in a Venturi meter, okay, which basically consists of a contraction in a pipe, okay, where the cross sectional area decreases in the contraction, the velocity increases, and when the velocity increases from Bernoulli equation, the pressure decreases, and from the pressure difference we found out how to calculate the velocity in the pipe, okay, and we solved an example of that. The second was the flow in a wire. Okay. This is basically an obstruction that is placed in a channel conveying a fluid. What is a channel whose width is much larger than its depth, a shallow channel if you will, in which within which you place an obstruction with either a smooth obstruction or a sharp obstruction, okay, and you measure the depth of water above this obstruction. Okay. Upstream, where the height is large, the velocity will be small, and as it passes over the obstruction, the height decreases and therefore the flow velocity increases as it crosses the obstruction. You measure the height far upstream of the obstruction, and from that the difference between the upstream height and the maximum height of the obstruction, you can calculate what is the flow velocity and the flow rate. The principle was that between a location far upstream where the velocity is small compared to the velocity over the obstruction, okay, in this case the total height is du, okay, between a location far upstream and a location that is on the obstruction, okay, if I write the Bernoulli equation, then the velocity is related to the difference in height, okay, because the pressure everywhere is atmospheric pressure, and far upstream the velocity is equal to 0, okay, and therefore you can find out what is the velocity at a given location, okay, as it crosses the obstruction. Okay, the velocity of course changes because the height changes as it crosses the obstruction, okay, and so we got this relationship for the velocity, okay, as a function of the height of the obstruction and the depth of the fluid layer, okay, above the obstruction, okay. D is the height of the fluid surface above the obstruction, and h is the height of the obstruction from the base level. So, we got an expression for the velocity and we got an expression for the flow rate in terms of the depth, and from this we found out that the difference between the upstream water level and the height of the obstruction is given by this ratio, okay, the velocity square by 2g plus the volumetric flow rate divided by the velocity. Note here the volumetric flow rate is a constant at steady state. It has to be the same at all streamwise locations, okay, at different streamwise locations. The volumetric flow rate has to be the same. The velocity changes as the depth changes, okay, and at the location where the depth is a minimum, okay, that is where the height of the obstruction is a maximum, okay. At that location the difference between the upstream depth and the height of the obstruction, okay, the derivative of that has to be equal to 0, and from that we got a unique expression for the velocity, okay, and from that expression for the velocity we can calculate what is the volumetric flow rate. So, let us solve an example to get a feel for the numbers. Okay. So, we have a broad crested okay, of height 20 centimeters, okay, is placed in a stream of width 0.5 meters. Okay. upstream the depth, okay, so this is the maximum height, okay. Of maximum height 20 centimeters is placed in a broad crested, is placed in a stream of width 0.5 meters. The depth far upstream is equal to 22 centimeters. Okay. So, what is the flow rate and velocity? Okay, what is the flow rate and the velocity? Okay. So, in this particular case, we know that du is equal to 22 centimeters, okay. H is equal to, the maximum height is equal to 20 centimeters, which implies that the difference du minus h is equal to 2 centimeters, okay. And therefore, from this expression, okay, the volumetric flow rate per unit length perpendicular, okay, per unit width, okay, has to be equal to 2 by 3 per 3 by 2 into, this is 10 meters per second square gravitational acceleration per half, into du minus h is 0.02 meters, 2 centimeters per 3 by 2. Okay. And this turns out to be equal to about 4.87 into 10 power minus 3 meters square per second. Okay. Note that this is the flow rate per unit width in the direction perpendicular to the stream. Okay. This is the flow rate per unit width in the direction perpendicular to the stream. Okay. Therefore, the total volumetric flow rate the total volumetric flow rate is going to be equal to 4.87 into 10 power minus 3 meters square per second into 0.5 meters, okay, which is meter cube per second. Okay, so that is going to be the volumetric flow rate. What is the velocity? Okay. Velocity is equal to v dot g whole power 1/3, okay, where v dot is flow rate per unit length perpendicular, okay, per unit width. Okay. So, this is going to be equal to 4.87 into 10 power minus 3 into 10 whole power 1/3. Let me put the units here. So, it is obvious that we are getting the correct okay. And this I am getting as approximately 0.31 meters per second. Okay. So, it is about 3 centimeters a second, 30 centimeters a second is the velocity that you get, okay, from this height of about 2 centimeters. Okay. And then you can calculate a Reynolds number based upon that height. Okay. The Reynolds number is the density 10 power 3 kg per meter cubed into 0.31 meters per second into 0.02 meters by 10 power minus 3 kg per meter per second. Viscosity of water in the denominator is 10 power minus 3 kg per meter per second. In the numerator, the density is 10 power 3 kg per meter cubed. Okay. So, this is approximately equal to 6200. Okay. So, okay, based upon the depth of water at the point where the velocity is maximum, okay, based upon the depth of water at the point where the velocity is maximum. Okay. So, this is also large. Okay. So, you can justify the approximation that inertial effects are dominant compared to viscous effects. and therefore, we have used the potential flow approximation. Okay. So, this is another example, okay, for flow metering. So, I have gone through two examples for flow metering, the Venturi meter and the flow over a wire. Okay. I will just complete a couple of more topics before we go on to a laminar flow in a pipe, and that is the macroscopic momentum balance. Okay. So, we can write a momentum balance equation for a macroscopic flow. Okay. So, for example, if I had a jet of water, okay, or a jet of some liquid, okay, that was incident on some surface. Okay. There was a velocity in with far upstream, you had a jet of diameter d that was incident, okay, and you want to find out what is the force that is exerted on this surface because of this jet of water, and do that in the inviscid limit where you can neglect viscous effects. Okay. Okay. So, if you write a macroscopic momentum balance, what it would say is that rate of momentum in, okay, minus rate of momentum out, okay, plus the sum of forces, okay, at steady state when there is no acceleration, rate of momentum in plus rate minus rate of momentum out plus force on fluid has got to be equal to 0. Okay. So, that is the momentum balance condition, okay. And this is a vector condition. Okay. Momentum in this case has to be in one particular direction. For example, in this particular case it will be the x direction if the flow is in the x direction. Okay. If the flow is in the x direction, this should be the x momentum in, x momentum out, and force on fluid in the x direction. So, you can write this balance individually for different directions. Okay. For the x direction you write one balance equation, for the y direction you write one balance equation, and so on. Okay. Okay. So, it's a vector equation. Now, we also know that the force on fluid, okay, is equal to minus of the force on object. Okay. The force on the fluid is equal to the negative of the force on the object. Okay. Therefore, from this equation I can find out what is the force on the object. Okay. Specifically in the x direction. Okay. Specifically in the x direction. Okay. Is equal to rate of momentum in minus the rate of momentum out. Okay. And this particular case, this is the x momentum. Okay. This is the x momentum. Okay. So, that is how you would calculate the force on a macroscopic object, okay, due to a fluid that is impinging on it. Okay. So, basically if we write this balance for a differential volume, okay, that looks something like this. Okay. Okay. Between the upstream jet, okay, which is in which the velocity is upstream jet where it is cylindrical, where the velocity is not affected by the presence of this wall. If the velocity in the upstream jet is v, okay, in the x direction, and then the velocity, the flow velocity goes parallel to the two walls. Okay. So, therefore, the flow velocity at the wall itself is perpendicular to the inlet velocity. Okay. So, that velocity is in the y direction. Okay. If we write a momentum balance, the force on the object, okay, in x direction okay, is equal to rate of x momentum in. Okay. The rate of x momentum in is the momentum density times the volumetric flow rate, okay, of fluid. Okay. The momentum density, x momentum density is rho times v, because velocity is the v is the velocity in the x direction. Therefore, the momentum density, okay, is equal to rho times v, and the volumetric flow rate has to be the velocity times the cross sectional area. Okay. The volumetric flow rate is the velocity times the cross sectional area. So, it is equal to v into pi d square by 4. Okay. So, this is equal to rho v times v pi d square by 4, okay, which is rho v square by d square by 4. Okay. That is the rate of momentum in. Okay. The rate of momentum out in the x direction in this particular case is 0, because the velocity is not in the x direction when it is leaving. Okay. When it is leaving, the velocity is not in the x direction. Okay. It is perpendicular to the x direction. Therefore, the rate of momentum out in the x direction is equal to 0. Okay. The rate of momentum out in the x direction is 0. The rate of momentum in is given by this. Okay. Therefore, the total force is also given by this. Okay. So, this is the way in which we can use a macroscopic momentum balance to calculate the force on objects. Okay. This of course assumes that there are no stresses that are exerted, okay, on the fluid. So, it is basically an inviscid approximation. Okay. Okay, this is basically an inviscid approximation, but with this we can calculate what is the force on an object. Okay. And finally, the last topic that I will cover is rotating fluids. Okay. A tank, okay. Initial height of fluid is h0, okay, and you rotate it with angular velocity omega, okay, and the fluid interface deforms, okay, and we would like to know how this interface deforms. Okay. So, if you are in a reference frame that is rotating with the tank, the fluid is perfectly stationary. Okay. There is no motion at all, okay, in the fluid. Okay. If you are in a reference frame that is rotating with the tank, then the fluid is stationary. However, there is still, okay, a deformation of the surface, and that is because of a balance between the gravitational forces that are acting downwards and the centrifugal forces, which tend to push the water towards the wall of the tank. Okay. The balance between these two basically gives you a deformed shape of the surface. How do we calculate that? We have to modify the Bernoulli equation to take into account rotation. Okay. In this particular simple case, because there is no there is no velocity in a reference frame that is rotating with the tank, okay, that half rho v square will be 0 in a reference frame that is rotating with the tank. So, I will have p plus rho g, okay, z, okay, where z is the height in the direction opposite to gravity, minus rho omega square r square, okay, by 2 is equal to a constant. Okay. where r is the distance from the axis in a cylindrical coordinate system, okay, where r is the distance from the axis in a cylindrical coordinate system. This is the additional term that is present for a rotating fluid. Okay. And so, this implies, okay, so I told you that P was the pressure energy, rho g z was the potential energy, half rho v square was the kinetic energy. Therefore, this is equal to the centrifugal energy. Okay. The centrifugal energy for rotation is basically equal to minus half rho omega square r square. Okay. The centrifugal force, okay, in the radial direction, the force in the radial direction is equal to minus dEr by dr, minus of the derivative of the energy is a force. Okay. So, this turns out to be equal to rho omega square r, which as you know is the familiar expression for the centrifugal force. Okay. So, this is the additional term in the expression for the rotating fluid, okay, and we can use that in order to find out what is the equation of the surface. Okay. So, if I look at different locations on this surface, okay, since the surface is open to atmosphere, the atmospheric pressure is the same at all locations on this surface. Okay. So, at all locations on the surface, P atmospheric, okay, plus rho g z minus rho omega square r square by 2, this has to be equal to a constant, okay, or alternatively rho g z minus rho omega square r square by 2 is equal to P naught minus P atmosphere. Okay. Now, at the axis at r is equal to 0, h is equal to the height at r is equal to 0. Okay. Therefore, okay, so let me just write this as h, okay, where h is the height of the free surface, where P is equal to the atmospheric pressure. H is the height of the surface where P is equal to the atmospheric pressure. Okay. Okay. So, that is the equation, the relation between the height, okay, and the radius r. Okay. That is the relation between the height and the radius r. Okay. We can find out this P0 from the value at, okay, r is equal to 0, h is equal to the value of h at r is equal to 0, okay, which implies that P minus P atmosphere is equal to rho g h at r is equal to 0. So, I substitute that on the right hand side, okay, to get rho g h is equal to, okay, plus rho omega square r square okay. If I get h is equal to h at r is equal to 0 plus so, this is a parabolic profile, this is a parabolic function in r, okay, it is equal to a constant plus something proportional to r square. Okay. So, therefore, height is a parabolic function, okay, with a minimum at r is equal to 0. Okay. So, how is the height related to the initial height? Okay. We know that the cross sectional area times the height is the volume in the tank. Okay. So, if the volume is maintained a constant, okay, if the volume is maintained a constant, that means that the initial volume has to be equal to the volume after the rotation has started. Okay. So, what is the volume of the water of the liquid in the tank in the rotating state? Okay. The volume is equal to this integral of this over the radial coordinate. Okay. That is equal to integral 0 to r. Okay. In a radial coordinate system, the differential area element is 2 pi r dr. We had seen this when we looked at a cylindrical coordinate system, into the height as a function of r. Okay. This is equal to integral 0 to r of 2 pi r dr into h at r is equal to 0 plus omega square r square by 2g. Okay. And you can do this integral here. So, this you will get, first term will be pi r square h at r is equal to 0, okay, plus the second term when I do the integral I will get, because I have an r cubed in the second term here, okay, I have an r cubed in the second term here, I will get plus omega square r square by 4g. Okay, so, this is equal to the initial volume, which is pi r square into h naught. Okay. That is the initial height before the rotation started was h naught. Okay. The initial height before the rotation started was equal to h naught. Okay. Therefore, this gives us h naught, h is equal to so this gives us h of r, okay, is equal to h naught plus omega square r square by 2g minus omega square r square by 4g. Okay. Just substituting for this, h of r is equal to 0, okay, substituting for this term, okay, in this equation. Okay. So, h at r is equal to 0 is equal to h naught minus, okay, omega square r square by 4g. Okay. I think I made a mistake here, it should be up of 4. Okay, and then I divide throughout by pi r square. Okay, so there is a factor of pi as well. So, this is equal to the initial height, okay, plus omega square by 2g into r square minus r square by 2. Okay. So, obviously this solution, so this solution h, the minimum value of h is equal to, okay, h at r is equal to 0 is equal to h naught minus omega square r square by 2g. Okay. Okay. That is the solution for h at r is equal to 0. Okay. So, now obviously this applies. Okay. So, h at r is equal to 0, I just substitute r is equal to capital R here, okay, and yeah, I am sorry, it should be 4. Okay. So, it is necessary that h naught has to be greater than this, okay, for okay, this solution to be valid. Okay. If h is less than that, what is going to happen is that, okay, the height is going to decrease to 0 at the center, okay, and then the calculation is different. Okay. Similarly, the maximum height, okay, h naught plus omega square r square by 4 g, okay, the maximum height has to be smaller than the total height of the tank. Okay. If the maximum height is greater than the total height of the tank, there will be a spillover from the tank, the volume will reduce. Okay. And therefore, in those cases you have to make a special calculation, assuming that the volume is not a constant, in order to find out what is the total height. Okay. So this is valid only when the initial height is such that the minimum height after rotation has started is greater than 0 and the maximum height is less than the height of the tank. What happens when either of these conditions is not satisfied? I will leave that as an exercise for you to solve. Okay. So with this we complete our discussion of potential flow. In the next lecture I will go on to examining laminar flow in a pipe using shell balances as we had done earlier for momentum transfer, for mass and heat transfer in a cylindrical coordinate system. I will use momentum transfer here with pressure variation along the length of the pipe. Okay. So, I will start this in the next lecture. I will see you then. Okay.